Now, with increase in this ratio ZLN divided by ZLD, we have increase in current. In effect, increase in load implies reduction in ZLD, which causes higher current drawn from the larger current drawn from the supply. That is what is this curve. Now, we have a critical value here. We have already discussed about this point P max where ZLN equals ZLD, which is an ideal point, but always the system may not be able to operate at this point. If not, it can operate near to this point. Anyway, beyond this point, the power transferred or power drawn from the supply reduces drastically. So it's always good to operate at a nearby point. Now here you can see the abnormal operation. Here after beyond this point, the system moves to abnormal operation, which means very high currents through the line, which may be at the verge of hitting the maximum current carrying capability of the line or the maximum current carrying capability of the system itself. And beyond this point, the received power is very less when compared to the sending end power, or the power that is transferred. Efficient power transfer is not there beyond this point. So this is considered as the abnormal point beyond this. Now, we have some nose curves also. I have already mentioned that we'll analyze the QV sensitivity of buses. Normally, we expect the voltage profile to enhance when injection of reactive power is increased to that particular bus. If it does not happen in that direction, then we say that the bus is voltage unstable, which means in a normal condition, we assume increase in voltage with respect to increase in reactive power injection on a bus. But if the voltage decreases with respect to increase in reactive power injection, then it's an abnormal condition or an unstable condition. So that is what is the importance of QV sensitivity that we'll see with the help of nose curves. Here you see the PR by PR max on horizontal axis and VR by ES on the vertical axis, and different curves are drawn with respect to different power factor values. That is, keeping the power factor constant, we are increasing the receiving end power. So what happens to the receiving end voltage profile that we are analyzing that. Now you can see that when PR is increased, I will increase, the current transferred will increase, which means line impedance into current drop, that will also increase, which will reduce the receiving end voltage, which will cause reduction in the receiving end voltage. That is what is seen here. Everywhere we see for any of these power factors, we see a reduction in receiving end voltage with respect to increase in receiving end active power. This is what is the PV curve. Now, there is a nose point for each of these curves. This nose point corresponds to the voltage collapse point. After this point, the voltage collapses. There is reduction in this region, and after this point, the voltage collapses. Now you see the locus of critical points. The nose point is the critical point. Critical point in the sense this is the maximum loadability point with respect to voltage instability, because the PR can be increased up to this limit only. This also maybe mathematically only we can say that the system can be loaded till this point. Before this itself, the voltage may collapse. Just before this itself, the voltage may collapse. That is that depends on the system also, system characteristics also. We will come to it later. But here you can see that when the power factor increases from 0.9 lag to 0.95 lag to unity, the critical point also shifts to the right side, which means the loadability of the system increases. And when it enters into the leading power factor mode, it still increases. And you can also notice that the loadability point corresponding to the voltage point at each time the voltage point is also increasing because the vertical axis corresponds to voltage. The voltage point is also increasing with respect to maximum loadability point. Right. So this is what happens when the power factor is varied, the power factor is increased, or rather the power factor is bettered, and this is what happens to the loadability and receiving end voltage. Now, another point which we'll see is with respect to a multi-machine power system. This is a multi-machine power system having 10 generators, 4 generators here, 4 generators here, and 1 synchronous condenser here. So basically 8 synchronous generators and 1 synchronous, 9 synchronous. This is 4 plus 4, 8 plus 1, 9 plus 1, 10. Now we are going to analyze the voltage profile of farther nodes in the sense 530, 520, 510. These nodes are load nodes which are farther from the source side. We are trying to analyze the voltage of these vulnerable buses in area 1. Now let's see the analysis. So we are going to take active power on the horizontal axis and bus voltage magnitude on the vertical axis, and we take three loading points A, B, and C. Of course, A is the minimum loading point. This is the in this curve, which is some near to some 90 megawatts. Then we load the system at B, which is some 170 megawatts, and then at the collapse point C. This is the critical point or the maximum loadability point of the system. So you can see here when the total active power in area 1 is increased, what happens is the voltage magnitude is also reduced. Voltage magnitude is reduced. The receiving end voltage here, the receiving end voltage means the load bus voltage. The load bus voltage is reduced. Now we'll see for different buses what is the effect of loading, that we'll see here. So what is done is step by step we are incrementing the loads at these buses 530, 520, and these buses we are increasing the load. You can see here the buses 530, 510, 160 and 200. Let's see first 530 and 510. Okay, these two buses. Similarly, we are increasing the load at different buses. Step by step increments we are doing. Now, according to the increment in active power at these buses, the active power at source should also be increased so that the power balance is maintained. So what we are doing is at each step we are executing a load flow so that we get all the output variable values. That means V530, V520, V510, V500. These are the voltages at buses 530, 520, 510, 500, etc. We want P, Q, V and del for all these buses. For these buses, of course, these are PQ buses because these are load buses. So at each increment, P plus delta P, whenever we increment this P with some delta P, the new P value assigned for the PQ bus is P plus delta P at each buses. Then we will again run the load flow. Then we will get the unknown variable values. At each stage, we are doing the same thing. Now, when you do like that, what happens here? This is a QV curve. This is not a PV curve. This is a QV curve. In PV curve, we have seen that in the horizontal axis, active power was shown, and in the vertical axis, voltage was shown. In the QV curve, in the vertical axis, reactive power injection is shown, and in the horizontal axis, we have bus voltage, different bus voltages. These curves correspond to different bus voltages. Now, as I already told, what we are expecting is a reduction in voltage with respect to reduction in reactive power injection and an increase in voltage with respect to an increase in reactive power injection at a particular bus. That is what happens in this region. Say we are considering this bus 200. This is a positive slope, right? So in this region, whenever the reactive power injection is increased, the voltage is also increased. But this happens till this point only. After this point, we have a negative slope. Negative slope in the sense increase in reactive power causes reduction in voltage. This is abnormal condition or unstable condition. So this is a critical point of the QV curve, beyond which the system is unstable. So this is the stable region. This is the unstable region. Similar to bus 200, the same phenomenon applies to all other buses also, 530, 510, 160, etc. Now, suppose this happens at the loading point A. Loading point A in the sense here. What will happen if the loading point is B? This scenario will change. The condition still worsens. Then what will happen? The sensitivity, the QV sensitivities will again change with respect to this active power loading. With the increased active power loading, for a small reduction in reactive power injection, there is a big reduction in voltage, bus voltage. That means indirectly we have a coupling between active power and bus voltage magnitude. We know that there is a direct coupling between reactive power injection to the bus and the bus voltage, but we have an indirect coupling between active power injection and not active power injection. It can be active power transferred. In a way, it is active power transferred. Active power transferred in the sense more active power is transferred through the line implies I into X line drop will increase, which will cause the reduction in receiving end voltage. Drastic reduction in receiving end voltage for increased active power loading. So QV sensitivity is affected for increase in P also. That is what. Okay, that is what is the point here. Now, the effect of transformer load tap changes on voltage stability. We'll see this. We have a source and an underload tap changer ULTC here and a load bus connected to the load. Now say the load is constant impedance. Then load increase means, as we have already discussed, load increase means reduction in load impedance, which will draw more current from the supply. Reduction in load impedance means increase in load admittance, right? Increase in load admittance. This will reduce the load voltage because increased current means increased drop, which will reduce the receiving end voltage. So to avoid this reduction in voltage, what will you do? That is why this ULTC is placed here. What is a purpose of this ULTC? To enhance the voltage profile, load voltage profile. So even though the voltage here is bad, the N1 by N2 or the turns ratio of the ULTC could be varied to improve the voltage profile at the load side. That is what is done by the ULTC. Suppose now we'll see what is done. The action of ULTC is to maintain this V load, right? So if there is increased current, there is increased drop. This increased drop will definitely reduce the voltage at this point, but this reduction will not reflect here. For that, we will change the turns ratio at the ULTC. So what happens now? Reducing N1 will boost the voltage at the other end, which means suppose initially N1 by N2 equals 1000 by 100, which means that the input voltage is stepped down by a factor of 10. Input voltage is this one. This is stepped down by a factor of 10. Now, if N1 is changed from 100 to N1 is changed from 1000 to 950. Initially, N1 is 1000. Now it is changed to 950. Then what happens? Then the factor of 10 now change to factor of 9.5, which means that the input voltage was stepped down by a factor of 10 earlier. Now the input voltage is stepped down by a factor of 9.5 only, which means the reduction in voltage is less and the receiving and the load voltage is enhanced. So N1 by N2 is varied and VR is improved. Okay. Now, what is the effect of this change in turns ratio on voltage instability? When the load impedance is referred to primary of the ULTC, then the primary referred load impedance could be ZLD dash equals turns ratio the whole squared into load impedance. Now, with respect to this equation, load increase corresponds to reduction in load impedance. Here, load increase corresponds to reduction in load impedance, which implies N1 will decrease, because whenever the transformer senses an increase in load and a reduction in voltage, increase in load in the sense that it decrease in ZLD and a reduction in voltage, it automatically changes the tap, changes the turns, or rather changes the turns ratio. So N1 is reduced. When N1 is reduced, ZLD dash will reduce. When N1 is reduced, ZLD dash will reduce by N1 squared, right? ZLD dash is reduced in the sense primary referred impedance is reduced. When primary referred impedance is reduced, what will happen? What is the effect of that? Impedance seen by the source is further reduced. When the impedance seen by the source is further reduced, the voltage is further decreased. Then again the new change in N1, because this decrease is again, this reduction is again sensed by the ULTC and it still varies further varies the N1 value, which will again which will again reduce the ZLD LD dash value. So this is a cumulative process. Whenever load increase is there, receiving and voltage reduction is there, turns ratio change is there, which will reduce the impedance seen by the source, which will further reduce the receiving and voltage, further reduction in further variation in turns ratio. So voltage is basically cumulatively reduced, and finally the voltage value may move to a very low value and the system may end up in an adverse situation. So this is what is a cumulative effect of underload tap changes in voltage stability. Now we will continue with the concepts of voltage stability in the next lecture. Thank you.